Okay. Thank you, Lubomir, for inviting me, and thank you all for coming. So today I'm going to talk about a brief overview of the field and a few tricks of the trade about how to train these networks. First of all, let's remind ourselves what is the goal here. So what we would like to do is to take any photo, do some processing, and then extract some features that represent richly what's in the image. So for instance, we would like the features to tell us that in this case, there is a window on the right, there is a chair on the left, nearby there is a monitor, which is on the top of the shelf, and so on and so forth. If we had such a descriptor, we would be able to answer many different types of questions, like what objects there are in the image, where they are, how they relate to each other, what kind of attributes they have, and so on and so forth. And answering different types of questions and reasoning about the image is one important component of what I would call an intelligence system. And obviously, this is a very, extracting a feature like that is very difficult because images live in a very high dimensional space, maybe 1 million dimensions and more. And it is very difficult to model distributions in very high dimensions. But fortunately, images actually live in a much lower dimensional manifold. And so, for instance, if you take face images, we know that we have about 40 masters in the face. And therefore, no more than 40 dimensions should suffice to model them, right? And so our task is to discover this manifold and to disentangle it, to linearize it. So to go back to the face image example, we would like this ideal feature extractor to have, say, the first component, which is about expression, the second about pose, the third about identity, and so on and so forth. So obviously, this is what I consider the holy grail of computer vision. And nobody knows how to design this feature, nor to learn them. But we do know that such a feature extractor should be very much nonlinear. And now the question is, what class of nonlinear functions shall we consider in order to perform this task? And as a good engineer, I like the divide and conquer approach. And I say that, well, perhaps, I know I have in my bag a dictionary of simple nonlinear functions that I know how to use. And now I'm going to try to combine them in some ways. So one approach is to take a linear combinations of nonlinear functions. And another approach is to instead do function composition. So the first approach is what we call, quote unquote, shallow. And kernel learning, boosting are examples of this. And the second approach is what I call deep. And now, while in terms of representational power, these two approaches are pretty much, they can perform the same input-output mapping, I claim that the second approach is potentially more efficient. And here is why. So when you do a linear combination, effectively, you do template matching. And now, if you consider that there is an exponential number of instantiations that objects can take because they can be in different position, rotation, scale, lighting, and so on and so forth. You need lots and lots of different templates, overall in very high dimensional spaces. While in the composition approach, we recognize that objects can be decomposed into parts, parts into subparts, and a single object at any layer of this hierarchy is represented by a few different features, not just one. And this is very important in high-dimensional spaces because it's much more efficient and you cover the space much better. And also, there is the concept of sharing. So for instance, here, you have that a wheel can be a part of a car as well as a truck. And so this approach is potentially much more efficient. And this is what we are going to use. And so at the end of the day, we're going to have a system that is composed by a cascade of nonlinear processing stages, and each stage is parameterized somehow. And the goal here is to tune the parameters internally in an automatic manner in order to perform well at the task at hand. The problem with this, the potential problem, is optimization. So now you have to solve an optimization problem, which is certainly non-convex. And so you may wonder whether it is something that you can solve at all. And one solution to this is to say, I fix the first layers and I just train the topmost one. However, this reduces the system then to the shell approach that we've seen before. And there is the problem of how to design well features and how to then redesign them when you change the kind of imagery that you are considering. Instead, what we do, we say, well, we are brave and we hope for the best and we're going to converge to a local minimum, but that's fine, as we shall see. And so in this perspective, we are going to have actually a joint system. So there is not really a separation between what is the feature structure or what is the classifier. You could even think that the feature structure is the first layer or perhaps the first 3 layers. But effectively, there is no separation. So we train everything jointly in an end-to-end fashion. So, and perhaps the most convincing argument for using deep learning is that it has been successful in many different applications, in speech recognition, vision, and it is already deployed in many commercial systems. And so the key ideas here are that we need to learn a nonlinear system. And one approach that is computation efficient is using a hierarchical model. And we are going to train this hierarchical model in an end-to-end fashion. So now, let's go into deep learning. So, many people talk about deep learning, but in my opinion, there is not a clear idea of what it is. There are a lot of buzzwords. It's a deep belief network. No, it's unsupervised learning. No, it's a convolutional net. I don't know. So there is no consensus of what is the definition here. Here is just my definition. I define it as any method which makes predictions by using a sequence of nonlinear processing stages. And the resulting intermediate representations that you get can be interpreted as feature hierarchies, and the whole system is trained, is jointly trained. And now this is a very large family that encompasses many, many different models. Some are probabilistic, some are not, some make use of labeled data, some don't, right? And so let me overview the field very quickly from in chronological order. So everything started in 1957 with Rosenblatt with the perceptron. So this is the precursor of the linear classifier that we have nowadays. And already at the time in the 60s, they tried to add layers. Just the problem is that they didn't have computers, and they were using like 5, 6 neurons. And they didn't have a learning algorithm to train multiple layers. And so basically, the field died, and people started working on symbolic rule-based systems. And the field came back to life in the 80s when with 2 big things. One is the use of modern computers to train neural nets. And the second is backpropagation, which is basically the algorithm that we still use today to train multi-layer neural networks. And that made a big difference. There was a lot of excitement about this. In the late 80s, 90s, this was applied also to computer vision application, in particular to OCR with the convolution neural network pioneered by Yann LeCun. And, but then around the mid-90s, late 90s, the field died again for a second time. And here the problem is that very much these systems were slow to train, were finicky, and simpler systems like, simpler methods like boosting SVM were performing much better, right? And so around those years, people pretty much stopped working on this stuff, and the people who were in this community started working on unsupervised learning. And in particular, the work, many people build on the top of the work, on the seminal work by Bruno Saus and David Field on sparse coding. And Jeff Hinton started working on what he called the restricted Boltzmann machine, which is a probabilistic version of an autoencoder. So an autoencoder is a very simple feature learning algorithm. It's just 2-layer neural net where you reconstruct the input for the sole purpose of learning some features. And restricted Boltzmann machine is a probabilistic version of this. And the breakthrough came in 2006 when he figured out that he could train very deep neural nets in a totally unsupervised way. And the trick was to start with a restricted Boltzmann machine, after you train it, you can just use it to map images into feature space. And then you use these features as data to train another restricted Watson machine, and so on and so forth. And at the end, you get a big graphical model, which is called deep belief network, that is trained in a totally unsupervised manner. And so the key contribution here is twofold. One is to be able to train very large neural nets with 1 million parameters on unlabeled data. And the other was the problem of getting around the problem of getting stuck in local minima. Because now you initialize with unsupervised learning, so everything is nicely initialized, and you would learn features that could be useful also for discriminating tasks. Later, people used this for many different applications, and the next breakthrough came from the speech recognition community, because those people basically discovered that you could actually train multi-layer neural nets with many, many layers from random initialization, provided that you had a lot of labeled data, and provided that you had fast, high-performance computing devices like GPU that could allow you to train for many iterations. And basically, since then, all major speech recognition labs are using neural nets as opposed to Gaussian mixture models in their core acoustic part. And the wave now has reached the computer vision community. Now people have rediscovered convolutional nets, pretty much with the same story. So we run on high-performance computing devices with lots of labeled data, and we get great results. And as Lubomir mentioned, there is the greatest achievement by Alex Krzyzewski and collaborators on this. So, the way that I draw these things is since that we went in circles many times and rediscovering the same thing over and over. So what did we do, right? Was all this unsupervised learning a false start? Did we really gain any understanding? Perhaps I'm optimist, but I think that it's just a misconception how we draw things. And I think as we go around, right, we learn, and everything is instrumental for the next step. So for instance, if you zoom in the convolutional nets, you see that this is pretty much the history. So it was invented in the 80s by Fukushima. He got the right architecture, but not the learning algorithm. That came 10 years later with Yann LeCun. And Tommaso Poggio, 10 years later, rediscovered the same thing from a very different perspective. And this work was actually very instrumental 10 years later because it was picked up by people in Jim DiCarlo's lab who had two main contributions. One was to make large-scale experiments to experiment with different architecture, and then also to plug layers that are biologically inspired, like the normalization layer. And that inspired the work of us when we were in Yann LeCun's group. And basically, we found that normalization layers, better nonlinearities, were very important to achieve very good results. And at the time, we were working on supervised learning, so we could match the performance of state-of-the-art methods on smaller data sets like Caltech 101. And then all these layers and these additions were explained from a theoretical perspective by Stéphane Malat, who is a mathematician and who has a very interesting work on scattering networks that where all these layers make sense and they have an explanation from the signal processing point of view. And lastly, the work done in Jeff Hinton's lab shows that by putting together all these ingredients, making things bigger and with more data that was provided thanks to the work in Fei-Fei Li's lab, we could achieve very good results. So everything was a necessary step, and nothing could have done without the previous achievements, I think. So one thing that we learned is, for instance, the following. So we always had the idea that the problem with training neural nets is that you get stuck in local minima, right? And so we had this mental picture of this loss function, right, in parameter space. And depending on where you start, you descend and you get into a local minimum. And there are different local minima that have different quality. But the work that is done in the speech recognition community and recently also on convolutional nets shows that actually whether you initialize the parameters with unsupervised learning or whether you initialize at random, it really doesn't matter if you have a lot of data. So this suggests that it's not really an optimization issue. Actually, what we have is that there are many, many local minima, of course, but they are qualitatively all the same. And the problem is long plateaus. And these plateaus are the result of a lot of symmetries. Symmetries that are derived from the fact that you can, for instance, permute all the hidden units and get the same input-output function. You can have, if you have a lot of parameters, you can have a lot of ties to break. It might take a long time to break them. And if you have units that are in saturation, then you have also very small gradients. And so these plateaus have a very small slope. And so my mental picture right now, and I think it is shared by many who work in this field, is that optimization of a neural net is very much like descending along the ridge of this Mont Blanc. And basically, you descend very slowly for a long time until you realize that if you just make a step on the left or on the right, you can go downhill much more quickly. But then the height of the valleys is very much the same. So it really doesn't matter. And so basically, the point is that if you stop training because you're training on a single core on a CPU early enough, you think that you are stuck in a local minima, but actually it's not. You just didn't train for long enough. And so in my opinion, optimization got even easier with larger data sets because even if you have points that are non-differentiable, as you get a lot of training samples, you get a smoother and smoother loss function. Also, right now, we don't use anymore units that saturate as much. And so the problem of small gradients is less pronounced. And we use normalization layers that also improve the optimization. And so in my opinion, here, the challenge is twofold. One is generalization. So with the current hardware that we have, we can instantiate networks that have 1 billion parameters. But now, how many training samples do we need to train a 1 billion parameter network, right? So if you are a statistician, you will say, well, you need at least maybe 3 samples per parameter, maybe 10. And then can you, how long is it going to take to train on a data set with 10 million samples, right? And so this points to the scalability issue. Another way to say it is that images live in a million-dimensional space. And now, how do you populate this space, right? So how do you deal with the Cursor dimensionality? And that points, again, to the scalability issue. So the main challenges are really generalization scalability nowadays, at least the way that I understand it. And going back to the space of machine learning methods, we can partition in many ways. And one way to partition it is to say, well, let's put on one side all the deep learning methods and all the shallow methods on the other side. But we can further partition in terms of which method uses label data, which doesn't, and we can further partition in terms of which method is defined in terms of a probability distribution, which don't. And so the point here is that deep learning is a very large family of methods, right? And the choice of one versus the other depends on your application, really. And in this talk, I'm gonna focus only on 2. One is a specific kind of deep belief network, and the other is the convolutional neural network. So a deep belief network is an unsupervised algorithm. So it's a density estimation method. It's a probabilistic model. And it is defined in a layer-wise fashion. So I'll start with the first layer. So the model is defined in terms of an energy function. And you get to the probability density function by taking the exponential of the negative energy, all right? And we start with an energy function which is a quadratic, so it's a Gaussian. And this is very good at modeling the correlations between pixels, right? So if you train a model like this, it will say that nearby pixels are strongly correlated, and correlation decays with distance, right? Now, this is good, but not good enough, because what you want is also to model the fact that sometimes there are edges, and you don't want to interpolate between pixel values that are across the edge. And so in order to deal with that, we introduce latent variables that modulate the coupling between every pair of pixels. And so in order to do this, we first factorize the inverse covariance matrix, and then introduce a diagonal matrix with latent variables. And so the graphical model, the toy figure of the graphical model is the following. So you have a pairwise Marc'Aurelio field where the coupling is determined by the state of the latent variables. In particular, if you have an edge, you set the latent variable to 0 so that you let these pixels that represent these variables, you let them independent, so to take any value that they want. And we further augment the model by having an extra set of latent variables that set the mean intensity for the pixel values. So if you look at the margin distribution, so if you sum over all possible configurations of latent variables, you get that this is like an infinite mixture of Gaussians, and that's because the energy function is a quadratic. So for every configuration of latent variables, you get a multivariate Gaussian distribution with a certain mean and certain covariance that is determined by the latent variables. And so it's like saying that, like in the plot on the bottom right, that you have this manifold of the data, and the way that you model it is by putting a bunch of ellipsoids. And each ellipsoid corresponds to a configuration of the latent variables. So it turns out that given the image, inferring the latent variables is straightforward. And that's because the energy function can be written as a sum over latent variables. You never multiply two latent variables together. And so computing the expected value of the latent variable given the input, so h given x, is straightforward. It's like a forward pass through a two-layer neural net. However, training is very tricky and very expensive, and that's because if you want to learn a proper density function, you need to normalize it, and which means that you need to solve so that p of x in order to be well defined, has to have a normalization constant, which is an integral over the input space x, right? And turns out that that's intractable. And so we need to resort to some approximations, and here we use MCMC methods. And these make the things tractable, but still very expensive. And after you train the first layer, you can use the probability of the latent variable given the input to map images into feature space. And then you can use that as data to train another graphical model, which is the one that you see at layer 2. That's a restricted Watson machine. And basically, we keep doing this for a few layers. And the whole idea is that you end up with a graphical model, okay? And this is an instance of a deep leaf network. I won't go into the details. You find more details in the paper that is mentioned here. Let me show you some results that you get by training this model. So after training on an unconstrained distribution of natural images, you can evaluate the model by drawing samples. And here on this panel, I show samples generated by baseline models. So on the top, you got an image generated by a Gaussian model. So you just model the power spectrum and lacks any structure. Next to it, there is an image generated by a model that fits the margin statistics of a wavelet decomposition of images. And so you see now you got edges, but they are incoherent. Below, there is a sample from a pairwise Marc'Aurelio field. So it's like the model that I described, but without latent variables. And next to it is a field of expert, which is close to what I described, but without some set of latent variables. And this is an image that is generated by using just one layer of our model. And now it looks weird, but basically it is somewhat better because now you have smooth surfaces with sharp boundaries between different regions. So it is much more coherent. These are other samples. And if you have 3 layers, you get something that is even more interesting. Now you have a little bit more variety of structure and things like this. So these are different samples. And so here the point is just to, to interpret what you learn. And it's kind of an advancement on how we can model natural images. We can apply the same thing also to face images, for instance. And on the top, you see, after I train on face images that were registered by the eyes, on the top, you can see the Markov chain Monte Carlo sampler in action. So every frame is taken 100 steps away from the previous one. And so you see that the model is doing a random walk in this space of face images, and it's generating faces with different expression, different gender, slightly different lighting too. And now that we have this generative model, how can we use it? So one way to use it is to use it to fill in missing pixels. So say that there is some occlusion, and say that you know also where things are. Now it is in the smiling mode. So say that you know where the occlusion occurred. What you can do, you have a P of X, and you can simply generate the missing pixels given those that you observe. And so on the bottom, you see what happens if you just use 1 layer, 2 layer, 3 layer, 4 layers, and then when you iterate a few times. And so you can get a pretty good reconstruction, and this image is from the test set. It doesn't know necessarily that there is symmetry in the face. It just learns it. And we basically applied this to different kinds of occlusions compared to other methods on the Toronto face data set. And our result is the first bar, which is better than the others. This was some experiments that we did more than 2 years ago. So to conclude, this is an example of what in deep learning we can do about unsupervised learning. So this is a pretty nice method, produces features pretty efficiently. It generates images of unprecedented quality, at least for the unconstrained distribution of natural images. It doesn't use labeled data. It produces features that are yet discriminative. The cons is that training is very inefficient because of the MC sampler. And it scales badly with dimensionality. And that's because MC doesn't scale well with that. At the end of the day, if you have a very large data set of labeled images, I haven't found an application yet where unsupervised learning is helpful in the sense that it really doesn't matter how you initialize things. And at the end of the day, if you're interested in learning features, then there are other feature learning algorithms that are perhaps more efficient, and in particular, those that are based on sparse coding. So that's pretty much, since this work, there has been many other kinds of work on unsupervised learning that have been improved in several ways. But from a practical application point of view, this is very much research work. It hasn't found a practical application. And it's not clear what's the use case for generating models once you have a lot of labeled data. And this brings me to the last topic, which is convolutional neural network. So throughout the day, you will hear a lot about this. And I think other people will go more in the details about what this is, but I assume that you are familiar. So it's basically the composition of a few stages where each stage is composed by a filtering layer, a normalization layer, and a pooling layer. And this is not so different from standard traditional computer vision approaches. For instance, SIFT can be seen as also being one stage of filtering, normalization, pooling, right? And then on the top of it, you add another stage for doing k-means pyramid matching and SVM. So it's not so different. So the main difference with traditional computer vision is that we actually tune automatically the parameters down to the pixels, right? So in principle, it is more powerful, and also in practice. So the first application of convolutional nets was OCR. Since then, there has been many applications that came out, texture classification, pedestrian detection, sim parsing, segmentation, so on and so forth, right? And the last one being image classification with last year ImageNet competition. But now, and these things have been deployed by Google, Baidu starting, and other companies too soon. But now the question is, we have this super powerful machine. How can we make a good use of it, right? So I'm going to conclude my talk with some tips about how to practical advices when you train convolutional networks. So many people ask, how should I choose my architecture? That's very task dependent, right? So I don't know. And that's usually picked by cross-validation. So you try different architectures and you pick the best one. For image classification task, we converge to the golden standard architecture, which is a bunch of convolution, normalization, pooling layers, right? And then some fully connected layers. In terms of how many layers, how many filters should I use, that really depends on how much training data you have, and also what is your computational budget, because the more layers, the more filters, the more expensive, and the more data you need. In terms of optimization, it's very simple. Nowadays, we train with simple online stochastic gradient descent, perhaps some mini batches with momentum. The way that I recommend to pick the learning rate is using Lombo2's rule. So you start with a very large learning rate on a small subset of the trained data. That will diverge. And then you half the learning rate up to when it doesn't diverge anymore. And then you take that value, you divide by 3 just to make sure that things are robust. And you make sure that by the end of training, you anneal the learning rate by a factor of 100. So that's the recipe. And in terms of the nonlinearities, what we call the rectified linear unit or half-threshold nonlinearity works really well. It produces very sparse representation. It's easy to optimize, doesn't saturate as much. And initializing the parameters is easy. You just need to make sure that the standard deviation that you produce at the output is pretty much 1, and the mean is 0. Ways to improve generalization. Of course, you reduce the number of parameters if you can by sharing weights. That's a great way. If you know also how things transform, how the patterns in the input transform, you can augment the data so that you get a much larger training set. You can inject noise in the input as well as in the hidden units. And one way to inject noise in the hidden units is to set them at 0 at random, and that's called dropout. Weight decay, of course, is another good way to do it, and also multitask learning. So it could be that you have auxiliary tasks that are related to the task that you're interested in, and unsupervised learning is one of them, and that could help you generalize better. Good things to know is the main cause of troubles when training these systems is bugs in how you compute the gradients, and numerical gradient checking can spot them out. It's useful to visualize the internal states. So the figure that you see here is just an image where the rows are different samples and the columns are different hidden units. What you expect is to find something that is sparse with random dots, right? What you don't want is something like this, where you have hidden units that are always on or always off, so ignoring the input, and they are strongly correlated. So that points to problems in how you optimize, how you initialize, or something like that. It's useful to visualize the parameters. If you train on natural images, we would expect the first layer filters to end up being kind of gabors. You don't want to find something that is noisy or filters that are too correlated or that lack structure. That points to some problems in how you optimize things. And Rob Fergus is going to show us this afternoon also how to visualize the higher layers. As a sanity check, it's good to test that when you train on a small training set, the error goes to 0. And it's good to track the error on the both training and validation set. Things that you should know when it doesn't work. So typically, the training blows up. So when that happens, typically the learning rate was just too large, or you had bugs in computing the derivatives. And numerical gradient checking is your friend in that case. The parameters may collapse. sometimes. And you see the loss goes down, but the parameters shrink to 0. And that points to a flaw in the design of the loss function that may admit degenerate solutions. So you should go back and redesign your loss function. Or the network may underperform. In that case, just make it bigger if you can, or look at how the optimization is done. So visualize the internal states, for instance, that can help. Or maybe the network is too slow. In that case, try to see where computation is spent. Maybe try to trim away the filters in the bottom convolution layers. Or just buy a newer version of GPU or try to distribute things. So to summarize, so deep learning is about learning hierarchical systems. And today, unsupervised learning is just a research topic at this point, doesn't have much practical applications. What really works well is supervised learning, things like convolution nets. In my opinion, optimization is not really the big issue here. The big issue is generalization and scaling. So if we have a billion parameter network, how many training samples do we need to fit it, right? And how can we scale to data sets of tens of billions of training samples? And to conclude, it's entirely possible, in my opinion, that a few years from now, we won't be using convolution nets. We have something that works so much better. And people have forgotten about this stuff. But I do think that no matter what, we still have to deal with the fact that we have to minimize loss functions that are non-convex. We have to deal with it. And we have to deal with the fact that the system that we are going to work with are going to be hierarchical. And these are two important ingredients that I think we will have to work with. And so I thank you for your attention. And I just want to advertise that we have a special issue on deep learning at IJCV. And you are strongly encouraged to submit papers. There is also a track for short papers that are more application. And this is with Jeff Hinton, Yann LeCun, and I are guest studied in this. So thank you for your attention. And I'll take any questions that you may have. Thank you.
Thank you. Questions?
Lubomir, you want to ask a question?
What can you tell us about the scalability?
OK, so scalability. I think the state of the art right now is to use GPUs. In particular, I think the state of the art has been set by Alex Krzyzewski nowadays, using a bunch of GPUs to distribute computation. People at Google, I read papers, they have built a distributed system that allows you to train using commodity machines, like 1,000 commodity machines. That's another way. I think it's very much an open question. So it's not entirely clear which way we should go. It's something that requires the interaction of system, machine learning, and optimization. And so it's going to be a joint effort. Yes?
Hello. OK, can you speculate if this kind of ConvNet architecture is good for any task beyond discriminative classification? For example, like labeling pixels, segmentation, 3D inference, and all this.
So I can say that there has been work on segmentation already. And that has been so for instance, Yann LeCun and his team has done work on segmentation. I think that's pretty comparable to state of the art. In terms of 3D, in terms of more other tasks, I think we need to probably change a little bit the architecture and the learning algorithm. So in order to kind of capture a little bit better the structure of the world, the 3D structure. And I think it's going to come soon. But it just also we need data that comes from video, that comes from other sources, and that is going to be also a challenge in terms of scalability, because then you need to process much more data. And so, but I think it's going to come. It just takes time to put together the pieces and to make it scalable.
Yes, back to your previous question. There is a distributed for the acceleration of GPU neural networks, and also you say there is GPU acceleration as well. So Google obviously is go to the distributed version. How about Facebook? Are you still exploring which is better, or you made your mind? If so, what was your decision?
Well, at Facebook, obviously we are trying all possible avenues, right, to make it more scalable. Also here we have tons and tons of data, so scalability is a major concern. And I don't think anybody has the definite answer about how to scale these things. And we need to try several directions, and probably it's going to be a mixture of a hybrid system or something, but it's something, I don't have the answer, right? It is something ongoing work.
Okay, thank you.
Last question.
Hi, I'm curious about what you talked about in generalization. Is there any work using deep learning networks that actually generalizes things like rotations and translations? Like if you trained on a bunch of whatever data you had, and then can it learn the abstraction of rotation or the geometric transformations? Because it seems like most of the work seems specific to certain objects, and I don't know if it actually understands rotations as a transformation in itself, but more.
So there is work on explicitly representing rotations. So the way that we achieve invariance is by saying training on samples that are slightly rotated, and then because you learn a many-to-one mapping, you're going to learn something that is invariant to rotation, right? And also because of the pooling, we get we produce representations that are invariant to rotation. But now there is another question of, if I want to be explicit about the rotation or the pose, how can I do that? And so there is some work about that. So Bruno Sausen has, and the people in his lab has done work on it, on unsupervised learning, where you are explicit about how things transform. Also, Jeff Hinton has done some work, but it's baby steps. So it would be nice to have that explicit. But,
Let's thank the speaker.
Thank you.